Okay, this is an interesting paper, and I love such papers. We are typically relying on technological promises, like let's say hydrogen production and very extensive use of hydrogen to replace carbon-based fossil fuels. And we say we'll make green hydrogen by using solar and wind, which are renewable energies. And all sounds nice, but we often are not being very clear about what the limitations are to achieve scalable production of these things, let alone the technological readiness of the processes themselves or the systems implemented to produce hydrogen themselves. Okay, so this is a good caveat in that sense. I have other such papers on biophysical limitations of carbon sequestration and so on. So global land and water limits to electrolytic hydrogen production using wind and solar resources. So electrolytic is basically where you are splitting something to get hydrogen out of it, like let's say water. Proposals for achieving net zero emissions by 2050 include scaling up electrolytic hydrogen production. However, this poses technical, economic, and environmental challenges. One such challenge is for policymakers to ensure sustainable future for the environment, including freshwater and land resources, while facilitating low carbon hydrogen production using renewable and wind and solar energy. So that's green hydrogen. We establish a country by country reference scenario for hydrogen demand by 2050 and compare it with the land and water availability. So obviously any scenario is going to include assumptions, and projections of hydrogen demand itself is going to be based on many assumptions, but it's still a useful exercise since everything for the future is being done with scenarios, including how much hydrogen we'll have, how much bioenergy, how much carbon capture we'll be able to do, and so on and so forth. Our analysis highlights countries that will be constrained by domestic natural resources to achieve electrolytic hydrogen self-sufficiency in a net zero target. Depending on land allocation for the installation of solar panels or wind turbines, less than 50% of hydrogen demand in 2050 could be met through a local production without land or water scarcity. Our findings identify potential importers and exporters of hydrogen, or conversely, exporters or importers of industries that would rely on electrolytic hydrogen. So who will produce hydrogen and export it, and who will use it and then export the products are, the two-way we have to think about it. The abundance of land and water resources in southern and central East Asia, West Africa, South America, Canada, and Australia make these countries potential leaders in hydrogen export. So Australia and Africa are also seen as potential exports of solar and wind themselves. So this is an additional potential advantage they could have. Wouldn't it be wonderful that the countries that have been typically poor, like Africa, can then become rich by being renewable energy exporters? They're paying a price for not being a big part of the CO2 emissions thus far, and then they can actually become solutions as renewable energy producers. Okay, I'll run through some figures, but you get the idea of what the paper is trying to do. So just focus on the message and not necessarily the details, because you'll have to go read the details of how the models are built and what assumptions are made and how the estimates are made for the various things like land needed, or hydrogen demand, and so on and so forth. Electrolytic hydrogen capacity in kilowatt electric per capita. So here you are talking about 2020, and here you are talking about 2050. So here are the countries going from China and US, India, all the way to Taiwan, and you are looking at methanol, ammonia, light industry, cement, refineries, transport, and steel. On this side we have hydrogen capacity, so direct electricity capacity, shown on this axis here. So you can see how so let's read the caption to understand what all the green dots are. Country specific hydrogen demand in 2020 and 2050. Hydrogen demand and capacity comparison for selected countries in 2020 and 2050. The figure illustrates the hydrogen demand per sector for the top 35 countries ranked by country specific demand in 2050 here. Okay. The stacked bars on the left side, y-axis, represent the per capita capacity required for electrolytic hydrogen production in each sector. So that's the per capita capacity here that would be required. The green markers on the right hand side y-axis represent ratio of the capacity required for electrolytic hydrogen production to the capacity required for direct electricity demand. So this is 0 to 1. So the ratio is 1 for many of these, for example here. To derive the capacity for direct electricity demand, so kW electric per capita, divide the capacity for electrolytic hydrogen on the y-axis in the left-hand side by the corresponding ratio of the capacity for electric hydrogen to direct electricity demand on the right side. The conversion factors used are 1 kilowatt electric is 0.62 kilowatt hydrogen, 1 kilowatt hydrogen is 0.03 kilogram H2, and 1 kilowatt electric is 8760 kilowatt electric per year. Countries are ordered based on their total hydrogen demand in 2050 as estimated by the projection, apart from Trinidad, Tobago and Qatar. So you have to see the supplementary material for details. So you get the idea. For example, China is here low in 2050 and lower in 2020 and lower in 2050 as well for these sectors in terms of the per capita capacity, and Canada is high here, Russia, and you can see that ammonia and methanol are high here. India is the third one here with a tiny bit of hydrogen demand and capacity, electrolytic hydrogen capacity. So you can see here Netherlands jumps up, and on top you have the ratio of hydrogen electricity versus direct electricity capacity in 2020 and 2050. Okay, so complicated, but you can just keep the general concept in mind. So land and water are the more important things. So you're looking here at land in meter squared per capita for solar and wind, and we are looking at millions of square kilometers total. So here we are looking at H2 scenarios in millions of tons per year in 2020 and 2050, and we are looking at for the world here. So the caption, let's read: land requirements to fulfill hydrogen demand in 2020 and 2050. Per capita country specific land requirements to fulfill hydrogen demand in 2020 and 2050 for solar and onshore wind. This is not offshore, is not considered here. The figure shows the land requirements to fulfill hydrogen demand A and B at country level per capita land requirements, and C and D. So C and D here in terms of global land requirements. So we are again looking at country specific and aggregate global quantities. Okay, in terms of global land requirements in 2020 and 2050 based on A and C for solar and B and D for onshore wind production. Okay, these are solar, these are wind. Countries are selected from the top 30 in terms of total demand of hydrogen in 2050 and are ordered according to the amount of eligible land for solar panels, excluding Trinidad and Tobago for scaling reasons, and interval bars represent the range of land required in 2050 based on the reference and the extreme scenarios of global hydrogen demand in 2050. So there are multiple scenarios generated. 400 million tons per year is the reference case, and 92 million tons per year is the smallest. 646 million tons per year is the largest. So those are the ranges. So you're going from 92, 400 being the reference scenario, and 646 being the largest. The gray areas and pink areas represent fractions and multiples of the eligible land as defined in their methods section, and are used for comparison with land requirements for hydrogen demand in each country. Different energy generation technologies require varying amount of land for the same amount of hydrogen demand. Okay, which means solar and wind are different. So you are looking at the coverage here: less than 1%, less than 5%, less than equal to 25%, less than 100%, and greater than 100% of the available land would be needed if you want to meet your hydrogen goals by solar or wind. So you can see that wind becomes very quickly limiting, because there are even countries in the range of 250 times the available area they have in terms of meter squared per capita. So you see that there are severe limitations for some. So eligible land coverage is the gray things, and land required for hydrogen production is shown in these red. So basically, if you are jumping here into 100%, here you are jumping into 250% for wind, for example, which means it's basically not possible for these countries to meet their electrolytic hydrogen production with wind, and it's a severe limitation even with solar, because if you need so much land of solar panel coverage for producing your hydrogen demand with production with the electrolytic approach, then obviously you are severely handicapped. So this, let's read the caption and come back. Water requirements to fulfill hydrogen demand in 2020 and 2050. So again, similarly, you have for solar, so this is water in tons per day per capita, and water in cubic billions of meter cube. So just two ways of looking at it. So water withdrawals for agriculture, industry, municipality, and water required for hydrogen production. So you can see that already just the agriculture, industry, municipality is going to be butting up against solar with less than equal to 5% here, 25% here. Very quickly you hit 100% and you become 500%, greater than equal to 500% for the countries out here like South Africa, Egypt, Algeria, Saudi Arabia, which are desert countries. And it's the same in terms of water demand for wind energy production required for H2 production and other demands. Okay, so this is the global again, so let's not go there. But again, it shows you that hydrogen production in red is going to basically add to many countries like here Trinidad Tobago. For most other countries, they are already overwhelmed by the demand for other industries like agriculture, industries, and municipality, which you can assume is mostly domestic use. Okay, so that's a very brief introduction. You can read the details in the paper, but obviously it shows that when we plan or dream about having green hydrogen to replace carbon or decarbonize the system, especially those that are not easy to electrify like the long distance transports and so on, we have to keep in mind what hydrogen demand could be like by 2050 and what land and water resources will be needed if we wanted to meet the hydrogen production with renewable energy like wind and solar. Okay, so again, there are base scenarios and extreme scenarios and so on. Further, land scarcity induced by hydrogen production, you are looking at 100% coverage, 10% coverage, and 5% coverage for solar, and similarly for wind. And you can see where the land scarcity begins to be significant, so greater than 2. So there is a scale for it. Land scarcity induced by hydrogen production in 2050 across countries worldwide, considering various fractions of land coverage for A, C, E solar and B, D, F onshore. So these are solar and onshore wind as before. The degree of land scarcity depends on the assumed eligible land coverage, which is what we had looked at here. Eligible land coverage, so F coverage for renewable technologies in each country, reflecting economic and socio-political constraints. So there are many assumptions involved. Notably, the lower power density of onshore wind leads to a significantly higher a number of countries experiencing scarcity, as you can see here. Countries depicted in gray lacked available data. The maps are created using some software. So what is the main message? There is the idea of wanting to produce hydrogen, assuming we will have ways of doing it with renewable energy at large scales. And then here we are only looking at the kind of energy production from solar and wind that would be required, and the land for deploying such levels of solar and wind, and the water demand that goes with implementing those energy productions. So this is not a good number in terms of scarcity of land and water. Okay, so this is exacerbation of water scarcity induced by hydrogen production. Again, H2 driven scarcity exacerbation with some scale going from 1 to greater than 5. MENA, Middle East, North Africa, which is a very arid water scarce region, India, China, etc. For solar and for wind, this is very severe for solar, which think of the contradiction. You think these are very prime locations for producing solar because they are dry and have large number of sunny days in a year, but on the other hand, the demand for water is going to basically exacerbate the situation tremendously, and it's also true for wind. Okay, so we must get real about the land and water limitations for producing solar and wind for our dreams of producing hydrogen with renewables, green hydrogen, to meet our energy demands. This is land and water scarcity introduced by hydrogen production in 2050. So land and water scarcity are here for 2050 for all countries, considering various fractions of land coverage for solar and wind, so 100%, 10%, and 5% coverage. And you can see land and water scarcity can be made much worse in some places, with land scarcity in some and water scarcity in some. Okay, so not good news for either solar or wind. These must be kept in mind when we keep dreaming about pathways to net zero, or staying below 1.5 or below 2 degrees C and so on. We must find a way to deal with these realities. To summarize, although the overall water demand for global hydrogen production varying between 3.2 and 95.6 billion meter cube is minimal compared to the availability of 10,560 billion meter cube of water worldwide, it is crucial to identify the countries and regions where hydrogen production may compete with other sectors and exacerbate land and water scarcity. You will soon have some ideas being thrown out saying water will not be scarce because we'll get water from desalination, and maybe we will deploy offshore wind and solar, but again, we will have to always remain realistic in terms of the associated biophysical limitations. Among these countries, Western European countries, Trinidad, Tobago, South Korea, and Japan stand out as particularly vulnerable in terms of resource scarcity. Trinidad and Tobago, heavily reliant on local oil and gas reserves for their industrial activities, may face challenges in producing the amount of electrolytic hydrogen from renewable sources required to sustain its chemicals. So Trinidad Tobago is one. Its chemical production, which is a key driver of its economy. Consequently, the country faces the risk of downsizing its chemical industry. Similar risks exist for South Korea and Japan. However, in these two countries, a larger portion of hydrogen demand is associated with the transport sector, which could be met through hydrogen imports from other countries. Conversely, regions such as West and Central East Africa, South America, Canada, and Australia possess abundant resources to meet their hydrogen demand and have the potential to become hydrogen exporters. Good news for West and Central East Africa, South America, Canada, and Australia. These regions are favorably positioned to capitalize on their resource availability and seize opportunities in the hydrogen market. While water requirements for hydrogen production is not expected to create water scarcity in countries where it does not already exist, except in Trinidad and Tobago, it does have the potential to exacerbate unsustainable utilization of water resources. In these regions, it becomes essential to conduct site-specific assessments to evaluate the sustainability of new hydrogen products in terms of water requirements. While geophysical constraints may not hinder the establishment of an electrolytic hydrogen economy in most countries, the scale of land required to achieve this goal is substantial. India, for example, private players and government are investing massive amounts in hydrogen, aiming to achieve green hydrogen, of course, but these kind of limitations are not completely thought out yet. However, social, political, and economic factors may render the extensive use of land for hydrogen production unfeasible, particularly in areas with limited land availability, relatively poor wind and solar resources, and/or expectations of high demand for electrolytic hydrogen. So think of bioenergy, which is also being promised for as a solution for decarbonization in the future, which is going to compete with water and land, and food security. And here you are all talking about producing green hydrogen with solar and wind, competing for land and water, and hence food security and other land uses and water uses as well. Okay, so just a good way to remember what we are dealing with. We make one plan without paying attention to the details, kind of a life cycle analysis, then we may create unrealistic future scenarios and keep dreaming about meeting global warming targets that just may not be reachable without some major game changers coming along. Okay.